Hi everyone. Today I would like to introduce our new designed Haechi QoS mechanism for one-sided RDMA-based storage system. This work is done by me and my advisor, Dr. Peter Varman. As the development of storage and network technologies, RDMA started to be used inside the distributed storage system to decrease the overhead of inter-server communication and the CPU interruption. In this paper, we focus on providing throughput reservation for storage IOs. RDMA includes two-sided and one-sided operations. Since two-sided RDMA-based storage access is similar to TCP/IP-based one, traditional QoS mechanisms can directly apply to two-sided applications. However, providing QoS to systems supporting one-sided IO services is a different story. Traditional QoS mechanisms can be divided into server-based and client-based QoS. The client-based QoS uses network latency measurement as feedback for QoS control, and it is not stable. The server-based QoS totally not work for one-sided IOs, since one-sided IOs are purely silent to target storage nodes. All the mentioned QoS mechanisms are not suitable to provide QoS guarantee for one-sided IOs. More details can be referenced in the paper. In this paper, we designed the first one-sided QoS mechanism called Haechi. Haechi is a token-based mechanism. It guarantees a client with sufficient backlog to process no less than reservation and no more than limit number of IOs in one QoS period. The total number of tokens in one period is estimated through the estimated capacity of the system. All the tokens are divided into reservation token and the global token. Reservation tokens are assigned to the QoS engine at client side. They can only be used by the assigned client. Client will return unused tokens in every checked period within the QoS period back to the global token pool. The global token are the remaining tokens after reservation. They are stored in QoS monitor at the storage side and can be shared by all the clients after they consume all their reservations. Now, let me use a simple example to show how Haechi works in one QoS period. A storage node provides one-sided IO services to 3 clients. Storage node dispatches 200 tokens according to the reservation of 3 clients. Client 1, 2, 3 reserve 80, 50, and 20 IOs as their reservation. The remaining 50 tokens per second are used as global. Each IO read consumes 1 token as it shows from client 1. After client 1 consumes all its reservations, if it still has pending IOs, client 1 then tries to get the global token from the storage node through silent RDMA atomic operations to process more IOs. This is the basic process of Haechi. Haechi also has a token conversion mechanism. As it is shown in the example, client 2 has unused tokens in some check period. It returns them back to the global token pool. Client 1, who has more backlog, can use them to process more IOs. Client will be forced to sleep and wait for the next QoS period if it is not able to get additional tokens. This example is scaled down of the real system. In the real system, capacity is at a million IO per second level, and we will get global tokens in a batch manner. Haechi uses 2 system violations as admission control mechanism to ensure that system capacity is sufficient to meet the reservation. The aggregate capacity violation guarantees that the saturated system capacity is sufficient to serve the reservation of all clients. The local capacity violation guarantees at all times the local capacity of any continuously backlogged client is sufficient to meet its reservation. This is a brief introduction of Haechi. Let's now see some experiments. We use 11 servers in the Chameleon to conduct the QoS experiments. One server is used to deploy the storage system, and the other 10 servers act as clients to trigger one-sided IOs. For the shown experiment, we use burst IO access pattern, which trigger all the IOs at the beginning of each period, and we use the ZIF reservation pattern. Bare system without QoS support is used for comparison. This slide shows the basic setup. The figure shows the ZIF reservation pattern across 10 clients. The results figure in the next slide will show a 30-second result. The completed IO distribution for ZIF reservation distribution is shown in the figure. This is a result when all the clients have enough backlog. The 3 bars in the right circle represent the results from one client. The first bar shows the client reservation, and the second bar and third bar shows the completed IOs in bare system and Haechi separately. Each small block in the bar represents the completed IOs in one QoS period. As it shows in the first and the second bar, in the right circle, client 1 cannot meet the reservation in bare system, but after we enable the Haechi, the reservation can be met, as it is shown in the third bar. The blue circle shows the result of client 6. Client 6 has much smaller reservation than client 1 and 2. Both Haechi and bare system can meet their reservation. The bare system finishes additional IOs beyond the reservation, as it is shown in the second bar. The Haechi system will adjust those IOs to high reservations clients like 1 and 2 to guarantee QoS. Due to the time limitation, more experiments in the list are shown and discussed in the paper. Finally, let me summarize the talk. In this talk, I introduced Haechi, which is a token-based QoS mechanism to support storage QoS on one-sided RDMA-based storage. Haechi leverages hybrid RDMA semantics to guarantee reservations and limits of a client with small overhead. For continuing work, we could easily extend Haechi to environment with multiple servers through BQ or ptrans. That is all about my presentation today. Thanks.